Hi everybody, welcome to the podcast Everyday Metallurgy, where we'll look into material that goes into batteries today. I have invited a good friend, Sven Fleischmann from BASF, to teach me about what goes in both the anode and the cathode and different kind of batteries. So stay tuned and enjoy the show with Sven. Thank you.
Hi Sven.
Hello, Peter.
Welcome to the podcast Everyday Metallurgy.
Thank you very much. Thank you for the invitation, Peter.
Yes. Thank you for joining. Sven, we are going to talk about metals in batteries because there is a lot of electrification going on and everybody wants to change their car from gasoline to electrical. But what is in these batteries and why do they work, and is there a risk? There's a lot of talk about we cannot get the materials, the fire, it cannot be recycled. There are a lot of things. So I would like some help on understanding what's inside these batteries and how they work. But first, can you give a fly-in to who you are and where you work?
Yes, so my name is Sven, Sven Fleischmann. I'm a chemist by education. So I actually come from more the soft matter materials because my background was on polymers. So I have studied the nature of polymers of soft materials for all my education.
Polymer, that's the dark side of material science.
It's the dark side. So in these old days, I was trying to remove the metals from any application, be it diodes or even in microchips. So everything was soft matter at that time because it was flexible. Cost of production are different and so on and so forth. But I came to the conclusion there is no workaround for metals. It clearly must be said. I mean, in metallurgy, clearly by a far extent, metal have their place in our daily life. That's why your podcast is so vivid. You have to come to an understanding. There is a place for polymers, for organic compounds, but there is a must-have for metals and for metallurgy. So after my education, I moved to BASF. It's a chemical company. Headquarter is in Ludwigshafen, Germany. And as usual, you start in central research. As a chemist, you join BASF and you start in central research. And in that time, I was designated to join a group that was engaged in the development of generation 4, next generation of battery materials for electromobility. So I was thrown into this water. I was not really familiar with that one. And I think it now from the retrospect quite remarkable because that was in the year 2008. So electromobility and the sense that you need improved battery materials was visible at that point in time. And I remember big organization formed like consortia with different industry players, European-wide alliances formed and so on and so forth. And there was really a strong momentum. And now I wonder where this momentum gone, because when you look at the country like Germany today, I mean, we are really lacking behind this one. I know that northern countries like Denmark, Norway is I think always on top, have way more advanced in electromobility than Germany. And I find this a pity because there was a lot of energy and investments involved into that, and it is a functional technology. I can clearly say that. Yeah. So, and when you start as a chemist in BASF, you have to get also familiar with the topics. I mean, it's always the same, of course. Yeah, and I started with the generation 4, and this is the lithium sulfur battery. So I will explain what that is.
Yeah.
But the benefit was of this lithium sulfur is, first of all, you have a higher energy density, so you have more energy output compared to classical, let's say, lithium ion batteries. But also, the raw materials are easier accessible. So sulfur is abundant. Yeah, it's a waste product even in some industries, so you can get it for low money. And lithium is also not so short as sometimes it is written. It's just a question on how you generate the lithium. So it was a strong quest in research to go for such an application with lithium sulfur. So we were benchmarking against the material that was called the lithium ion battery.
Yeah.
So the lithium ion battery is the one, as you know, is the battery type that we use widely today.
Yeah. If we go longer back and look into the history of batteries, I remember when I was a kid, there were these small batteries you could put in your Walkman. What was in that, and why is that not used any longer?
Yes, so I think a more modern battery was nickel metal hydride. These were batteries that were, I think they are still around today because they are somewhat a cheaper version of lithium ion battery. It's in fact a different type of battery. So they are really safe. That needs to be said because the solvent, the electrolyte being used is water, so it's not flammable. It's a very convenient material, and it has a very good cyclability. So there's one term that we need to understand, and this is the term of cyclability. That will come across this podcast quite often. So it's characteristic for how often you can charge and discharge a battery. Charge and discharge, and discharge. So, and usually these cycles, they must go into the thousands of charge and discharge cycles. Otherwise, really, the system is not good. And these nickel metal hydride batteries, they had a very good capability there. So they could, or you still can, cycle them tens of thousands. So very stable.
Yeah.
The disadvantage was daily life experience, right? It has not the energy density, to separate that and to make it really use for a mobile society. There is another term that we need to understand, and this is the energy density. That's a term that comes across the battery a lot. Energy density is measured in watt hours per kilogram. Watt hours per kilogram.
So it's not per volume.
You can also calculate by the volume, but very often you refer to by the kilogram, because it's anyhow volume is quite comparable then. So they have all inorganics. It's a very stiff and rigid formation, so it's more or less the volume stays constant. So you refer to the kilogram. And these nickel metal hydride batteries, they had an energy density of probably 80 watt hours per kilogram. And then there was a mild jump in with the lithium ion batteries. And lithium ion batteries, they are around for many decades. I think they were invented by Sony in the late 80s, early 90s. They were also commercialized there. Of course, as you said, for the Walkmans in the old days, you needed to power these portable devices by batteries. And so these batteries were around, and their potential was not really recognized for a long time. And there was a graph that I remember that now. I cannot show it to you right now. But when you talk about electronic devices, storage devices, I mean, famous known is Moore's law. So every 18 months, you double the capacity of a computer chip. So every 18 months, doubling the storage capacity of a computer chip. So this is This is Moore's law. And, that's an exponential growth over the years. So whereas, the storage capacity for microchips, grew exponentially, the storage for energy was very flat for a long period of time. There was a linear growth, only very, very flat growth.
Okay.
So you moved on from, let's say, 20 watt hours per kilogram to 30 to 50. So nickel hydride batteries then 80. And now with lithium ion batteries, we are with 120 watt hours per kilogram. So, it's a very, very slow progress.
Yeah.
And that is the challenge still of today.
Yeah. If we take one step back and look into the battery, how is a battery built up? There's a cathode, there's an anode, there's a separator, there's a house. So can you describe how a battery is built? And I don't know if you will do it on the fly. So how is it manufactured? Is it powder bed? Is it rolled? Is it sheet formed? So to give some insight in the process to produce a battery and what kind of materials they use to make the batteries.
Yeah, first of all, I think it's interesting to know batteries is not like a wet experience. There's not much liquid involved. When I started, I thought, oh my God, it must be really like a lot of electrolyte, but it's not the case. The electrolyte is soaked by the porous material, so you don't even feel the presence of an electrolyte. That's quite a remarkable effect that I experienced when I first opened a cell at that time.
Yeah.
Yes. So what components we are having? So we have the anode. We go from left to the right, let's say. We have the anode, which is typically then, let's say, the ion donor. Then there is, in the middle is the separator, and at the right end, then there is the cathode material. And in between, there is this electrolyte. The electrolyte is needed, it's a liquid. The liquid contains ions, lithium ions, for instance, that provide the migration of charges, during the charge and discharge process. You need a separator in between because if you touch anode and cathode, you have a shortcut. So you would run into problems. Even your battery would start to burn, something like this. So
that's a collapse.
That's a collapse. So you need to avoid the touch. That's why you have a separator. And the separator is a polymer foil. It's a membrane, better to say. Very often it's something like Nafion. It's a very special type of separator material that is porous. So it has channels from left side to the right side. So it's soaked by electrolyte and the ions can migrate through this membrane.
Okay.
That's it.
And how, if we start with the anode, what materials are used for the anode?
Yeah. So for lithium ion batteries, you have graphite as an anode. Graphite is a relatively cheap and abundant material. Of course, you need to have, and that's always secret, of the different companies. You need to have different morphology of this graphite. And what graphite is, when you bring it down to the chemical viewpoint, it's carbon, and this carbon is in a layered structure. So what happens when you charge your battery? So you have the lithium coming from the electrolyte, lithium ions coming from the electrolyte and from the cathode, and they go into the galleries of this graphite. So they are intercalated, people call it. They take interstitial places in these galleries of the different carbon layers. So you could see then, with microscopes or with some electrochemical effects, that when a lithium ion is seeking its place in these galleries, that the distance of these galleries, it grows. So it has a certain nanometer distance, angstrom distance, and it goes a little bit higher because it feels the presence of the ion, so to speak. So this this is graphite, and with graphite, everybody's quite familiar with that. I mean, it's a black material. So how you prepare is I would say, is also a art by itself. On the paper, it looks very simple, but in details, there are many obstacles that need to be overcome.
Yeah.
So you start with a slurry. So you prepare your electrolyte and your graphite components, maybe other components, and bring it in a suspension, steer it, and then you can doctor blade it. You can roll it on copper or aluminum foil.
Yeah, so tip casting.
Correct. Some casting process. Yeah.
Mm-hmm.
And then, of course, it's dried, and on drying, a lot of things can go wrong. You may have cracks because of evaporation too fast or so. So this is all a very, delicate process that needs to be controlled by the engineers in production. But it's state of the art. It's done very reliably. No problem about that. And now people are moving to other sorts of anodes. So they are trying to find alternatives to these lithium graphite anodes, because you would like to increase the energy density that we have talked about of these materials. So what you can have is then, for instance, metallic lithium. Metallic lithium has by far a higher capacity and energy density than this graphite, by far. So you can use lithium foils, for instance, ductile foils. You can roll that, make it very, very thin, attach it on a current collector. Again, could be a copper foil, and then you have metallic lithium. The point with metallic lithium is it is very reactive. Remember we know this experiment in high school, where the teacher would throw sodium in a in a glass of water, and then it like burns and has a very agit reaction. And the same is with lithium. So it must be handled with cares. And anyhow, moisture, water, even for graphite anodes, is a big problem. So these battery factories, these fabs that are being installed, they are in dry rooms. So the humidity must be very, very low. People are referring to a dew point. So it's when basically the temperature, when water condenses, you have this effect with a cold glass of water in summer, then you're outside, the moisture precipitates. So, and here the atmosphere is so depleted of water moisture that the dew point is minus 60 degrees C. So it's a very dry,
low.
It's a very dry environment. And this is especially needed for these lithium foils when you have metallic anodes. So that is one, I would say, research topic. I would say it crossed the research already. So we have for sure, startup incubator status of these anode types, and we will see probably in the next years application of these metallic lithium anodes. There is another approach that is also followed severely by many companies, by many players, universities, and so on and so forth. And this is the use of a silicon anode. So you have metallic or semi-metallic silicon. It also has the ability to accommodate lithium ions, and the capacity, the storage capacity of silicon for lithium is extremely high. So that is an extreme advantage. However, the problem here is there is a huge volume expansion coming along with this process. And that is a problem, if you design batteries, because if it's expanding, it's shrinking, there's a lot of mechanical agitation.
So it will crack?
It will crack, exactly. Then the battery performance goes down. So this is the problem that I think is not fully solved yet. So here people are thinking of like sponge-like structures, so that you have silicon that is not like a big bulb or so, a pure mass, but or a sponge-like character, high porosity, so that you can work against this volume expansion somehow.
Is this with silicon? I've seen somebody call it stone batteries. Is that it? Because they have taken the silicon from stones. It's all around.
Maybe that's the case. I haven't heard about this one.
Okay.
It could be, yeah, that you take, sand, stone, yeah, and then you do this reaction. You have to deoxidize it. You have to reduce the silicon oxide and then form pure silicon. Could be the case, but you essentially need pure silicon chemically, like Si.
Yeah.
That's
but it's not a wafer. It's
not a
just the
wafer.
silicon. No.
It's not a wafer. It's a different style of implying that. Yeah. I haven't really seen these batteries in action. I have seen a lot of metallic lithium ion or metallic lithium anodes working in action, and another problem with these metallic lithium anodes are their reactivity, as I said.
Yeah.
So
Sven and I, we talked about the stone battery. In fact, it's called the rock battery. It's an invention made by a team from the Danish Technical University that has developed a battery based on potassium silicate. Potassium silicate is abundant material. It's all over. So compared to lithium, you can just dig it out of the stone. It's a solid state battery, but it's still pretty low TRL levels, so it will take at least 10 years before you see it in real life. But some of the advantage to this is that it is not affected by humidity or air, so you can make very thin structures without risk of burning. So this could be a game changer if they succeed in developing it. But back to the show with Sven.
So in a classical battery, let's go back to the single unit cell. A cell, you need this electrolyte. Electrolyte again is a solvent. Very often you also need additives, that again are very secretive. They have different functions, to perform a good cell chemistry. And the problem is that with metallic lithium, it's all reacting at the lithium anode because it has such a high, it is so willing to give away an electron, and it reacts with these components easily. And over the time you see, not over the time, you see quite rapid degradation.
Okay.
So you must look for a way on how to protect this lithium surface. And there are many concepts around. I mean, you can think about a protective layer, and this protective layer could be a soft layer, like let's say a polymer, a type of separator material, but could be a ceramic that enables good lithium ion penetration. And so this is a very demanding task for engineers and for material scientists to find such material that are stable in this potential environment of a working lithium anode, and on the other hand allow lithium ions to penetrate and get in touch and to reach this surface. Yeah. So there are concepts, and one of the concepts that you have strived before is the all solid state battery. So you can best work then with this metallic lithium if you don't use a liquid electrolyte at all. Yeah. And these are the concepts that I would say are the most promising. So because you reduce the weight a little bit, you simply remove the electrolyte. That is one saving, but the key essence is that you can work with metallic lithium, and that has this high storage capacity. And by removing the electrolyte, you omit all these side reactions, the decomposition of materials on this anode. So that's the big thing about that.
What's the power density of a solid state battery compared to the other? You said 120 for a.
Yeah. So, I mean, this can be 10 times as high.
Wow.
I mean, so the storage capacity for metallic lithium, or let's let's give the example of a lithium sulfur battery. So lithium, metallic lithium on the anode side, and you have sulfur as a cathode material on the other side. So that has a storage capacity, the energy density of 2,600 watt hours per kilogram. So we are coming from 120 watt hours per kilogram for classical lithium ion batteries to 2,600. So that would be a massive jump.
Yeah.
Massive jump.
I would like one of those in my car.
Yeah. So you could reduce, your battery weight significantly,
Yes.
and have, really extended driving experience with such type of batteries. Yeah. The problem with the lithium sulfur cell is the following. So here, for sulfur, how the battery is functioning, you need a liquid electrolyte. You cannot work with lithium sulfur with a dry cell with this solid state batteries. That's not possible. The sulfur in this chemical reaction needs to be dissolved, otherwise the battery does not function. So, and when sulfur gets dissolved, I mean, you have a lot of problems creating. So on the one hand, you remove mass from your cathode. So the cathode is kind of also collapsing. Yeah. So you need to provide some structure, and everything may work under pressure. Yeah. So you must provide something that the battery is not collapsing. And the second thing is that sulfur is migrating towards the anode, and then maybe oxidized, may undergo side reaction and is deposited on this anode. And this then again is a problem because it may not be redissolved in your next recycling step. So it may stay on the surface and it's simply then gone for the next cycling. So what we see today is a very short cyclability of these lithium sulfur batteries. So I mentioned that you would like to see thousands of cycles. So when you have a smartphone, over the lifetime, you're going to charge and discharge it thousands of times. So every year, 365 days, I would guess. You have it for a number of years. So you need more than 1,000 cycles for a good battery lifetime. And with lithium sulfur, I don't know the latest numbers, but they are far below 1,000. You are probably reaching some hundreds, I would guess. But this, I think, is still not enough. So there was some strong impetus 10 years ago when everybody was, jumping onto this lithium sulfur. I think this energy has a little bit depleted. And in fact, the next generation could be this all solid state battery. And then it's going to be a metallic lithium anode, and then any type of cathode material that gives a good energy density. And then I would say we are back with metallurgy.
Yeah. We'll take a short break here because our heads are pretty filled up now. But when we return with the next episode, we'll dig deeper into the cobalt issues because batteries, as known today, contain a lot of cobalt, and cobalt is an issue. But that will be next episode. Enjoy the break.